So we're starting a new chapter now called Solubility and Complex Ion Equilibria. And here we're going to spend our time talking about all things that affect the solubility of various ionic compounds and how sometimes the solubility could decrease or could increase depending on what other ions are present. Now we're going to start by just talking about why this is important. And the main reason is because there's a lot of different applications where solubility is a factor. So for example, when we're preparing different types of industrial chemicals, such as sodium carbonate, which is used in laundry and which is detergent preparation, that's requiring precipitation reaction. A lot of applications in biology based on making sure that certain things precipitate or certain things don't precipitate. For example, in tooth enamel, actually, what you have is a compound that's called hydroxyapatite, and it is generally insoluble in water, but if you have acid present, then that salt is going to be more soluble, and we'll talk about how pH affects solubility later on in this chapter. And so that's the reason why we try to avoid some of these food, because they produce a lot more acid, which then cause the dissolution of the tooth enamel. And then there's applications like imaging of X-rays, where you have to ingest a compound that is insoluble because that compound contains barium, which then can absorb the X-ray, so thereby providing a contrast in the image. And so there is a lot of applications, much of which I'm not mentioning here, but we're going to have to think about some of these concepts associated with the equilibrium of soluble salts in order to be able to explain some of these applications. So we're going to start with just something from a prior course, Chem 11, and that is the solubility rule. Previously, you've been asked to memorize this list of rules so that you can apply them quickly in a sort of black and white type scenario where some salts are considered soluble or some salts are considered insoluble. And so the soluble salts are what we say will dissociate completely into the ions, the separate ions, of when we put them in water. For example, things like NaCl would just form Na plus and Cl minus. And then we have insoluble salts where we just say they don't dissociate at all, and we just see the precipitate. So for example, if we write AgCl, we would say that that's just solid. And we don't necessarily have a more in-depth picture than that. But in Chem 12, in this class, we're going to go further and describe how some salts are going to dissociate, even though they might be categorized as insoluble in Chem 11. And the question is how much of that ions are actually present in solution, and we can calculate them. And that's really what we want to spend quite a bit of time doing in this class, because even at small concentrations, some of these ions become important in chemistry, okay? But it is useful to remember the solubility rule. So one of the things I want to emphasize is make sure you go back and rememorize this if you have forgotten, because that's the one that's going to help you, at least be able to tell if you're given a salt, whether that's going to be soluble or that's going to be insoluble. And then the insoluble ones are the one we're going to spend time talking about here. Let's get started by just differentiating the different types of salt that we have. So we have soluble, we have slightly soluble, and then we have insoluble. So generally speaking, the way we categorize them in different groups is just on how much of it dissolves when we mix them in water. So a soluble salt would be something where 10 grams per liter or even higher is the concentration. So if you take, for example, sodium chloride, more than 10 grams of it could dissolve per liter of solution. And as a result, we call this a soluble salt, sodium chloride soluble salt. There's a lot of other salts that have that particular behavior. We have slightly soluble salts where the solubility is somewhere between 0.1 to 1 gram per liter. And then we have insoluble salts where solubility is less than 0.1 grams per liter. Note that insoluble doesn't mean that there's nothing at all that dissolves. There's some quantity that dissolves, it's just very little. And again, that's a slightly different picture than you might have in Chem 11, where we just say that if it's insoluble, you just write them as precipitate being formed. Going back to the soluble salt, the key assumption we make in these soluble salts is that all the salt dissolves, and because they all dissolve, they also completely dissociate to form ion. For example, in a solution of 0.1 molar NaCl, we would assume that all the NaCl, once we mix them with water, becomes aqueous NaCl, and then the aqueous NaCl would then not stay together, they will completely separate out into Na plus and Cl minus ions. So if we have 0.1 molar NaCl, we would in the end have 0.1 molar Na plus and 0.1 molar Cl minus floating around. So we consider the dissociation irreversible. In other words, it just goes to completion, just like those large K reactions, okay? And then we have the slightly and the insoluble salts. And in cases, the idea is that not all of them form ions. So we have some amount that form ions. So the reaction is pretty similar. This should be an arrow here going from the solid being mixed with water, and then it forms aqueous version of the salt. But then again, they just break apart to form separate ions. However, this process where the solid dissolves into the aqueous form is just not a whole lot. So there's only a small percentage of it that actually converts into the soluble form. Now, as soon as it gets to the soluble form, then it would just dissociate to form those ions. Okay, so these species don't really exist, or it's assumed not to exist in solution. Okay, in the sort of typical approach to this type of calculation. Because we assume that these species don't exist, the reaction is just written bypassing that particular part. We start with the solid, we go directly to the ion. So the reaction you'll see most often would be something that's written this way, the part that I just highlight. Again, there's an equilibrium here, which is between the solid version and the separated ion. So we kind of bypass that middle portion, the soluble dissolved salt that are still in the complex. Now, don't want to take too much time with this, but do want to point out that that's not really true in reality. In reality, there's some of these complex or partially dissociated ions that exist. So, for example, if we take lead chloride, put them in water, we don't only see lead and chloride ions. Those are the ones we assume exist when some of the lead chloride dissolve in water. But there's actually also some lead chloride that are aqueous, and there's some lead chloride plus ions with just one chloride ion stuck there that are present. But because it's so complex to have to analyze all of the ionic species and partially dissociated species, we typically just assume that only the lead ion and the chloride ion exist, and we use our calculation based on those fully dissociated ions. Okay, so now let's talk about how to quantify the solubility of insoluble salt. Okay, so we know that they're not completely insoluble, meaning that there's some small portion of it that actually dissolve in water and then some ions. So how do we quantify how much ions we have? One way is by calculating something called the solubility. This is a term I've used earlier. And it just means what is the maximum possible concentration of that salt at a certain pressure and temperature combination. Or what's trying to quantify is really these species right here, the soluble version of that salt itself in terms of molarity, right? So because it's aqueous, I can calculate the molarity of that salt. So that's what we refer to as solubility. Of course, the solubility of that salt is then connected to the concentration of the ions that we have. So you can see that because it has a one-to-one stoichiometry in the case of calcium sulfate, that whatever the concentration of the calcium ion, it's also the solubility of the calcium sulfate salt, okay? So that's just something to keep in mind about the meaning of the word solubility. You can express solubility either as grams per liter, as I did earlier, or in molarity, which is just moles per liter, and that's called molar solubility. So for example, if I have a solution of 1 millimolar calcium sulfate breaks apart into calcium and sulfate ion as a one-to-one stoichiometry, then that also means that I have 1 millimolar of calcium and 1 millimolar of sulfate ion. It's slightly different if you don't have a one-to-one stoichiometry. So an example is with PbCl2, where it breaks apart into Pb2 plus, 2Cl minus. And so in this case, there is a 2-to-1 stoichiometry with the chloride. So if I dissolve 1 millimolar lead chloride, then I'll get 1 millimolar lead ion, but 2 millimolar chloride ion. So this is straight stoichiometry, but something to keep in mind as we're going to go into calculation later on. Another way to express solubility is by using K value, called KSP in this case. So the SP here stands for solubility product. It just means that this is a K that is specific for the solubility type reaction that we're going to be talking about. And again, the general way this reaction is written is you would start with your solid at the left side as the reactant, and then it's a reversible reaction to the aqueous version of the ion. And again, we kind of skip that aqueous salt that's formed before it breaks apart the ion. So we just write the reaction this way. So the KSP is just the K value of that reaction. You can see if I'm just writing it that way for my AB salt, it would just be A plus concentration times B minus concentration. The solid doesn't factor into the KSP expression, so that's pretty much it. Here are some examples. of KSP expression for different types of salt with different types of stoichiometry between the ions. So hopefully you can see how KSP expression could be as simple as the one that I just gave you with that AB, or it could be as complex as this calcium phosphate salt, which has calcium raised to the third power and phosphate raised to the second power. So let's look through a couple of examples on how to connect solubility and KSP together, because they're both the same measure of how soluble a salt is. So in the first one here, we're looking at how to calculate KSP if you're given the solubility of a salt. So in this case, we're told solubility of calcium sulfate is 0.67 grams per liter. We want the KSP. Now, keep in mind that solubility is the concentration of the soluble form of salt at equilibrium. So imagine taking a salt that is a solid, okay, and then putting it in a container that has water in it, and then after the salt dissolves, now have some concentration in it, and that concentration of the dissolved salt, put brackets around it, that is your solubility. It's equal to solubility. Now, of course, what happens with salt is it doesn't stay as dissolved salt. It separates or dissociates into its individual ions. So then what we have to do is calculate the ion concentration and then connect it back to solubility. And that's what I'm going to do here. So I start with CaSO4, separating out into calcium and sulfate ion. And then the KSP of that reaction has the following expression, right, which is just calcium ion times sulfate ion concentration. As I just said, the calcium sulfate that is dissolved is what we call solubility. So what we're trying to do is somehow connect that to the ion concentration, but as it happens, since this is a one-to-one stoichiometry between the salt and the ion, then whatever the concentration of the ion is, whichever ion you choose, happens to also be the solubility of the salt. So all we need to do is get the solubility of the salt, connect it to ion concentration, and then calculate the KSP. So the solubility of the salt is just going to be 0.67 grams divided, in this case, by the molar mass of the salt. It's very important that it's, because again, the solubility is defined as how much of the dissolved salt is present in solution. And so if you do that, you get this number, which is 0.00492 molar. That happens to be the same as the concentration of the calcium ion, as well as the concentration of the sulfate ion. Now, since our KSP is just the product of those two concentrations, I can square them together and I get 2.42 times 10 to the minus 5 as my KSP value, okay? In the second question, we're now given KSP of lead iodide, and we're being asked to calculate the molar solubility of the salt itself. So now we're kind of going the other way. We have KSP, we're trying to calculate solubility, but the idea is the same. Here on the right, I'm showing the work. I have the reaction, and here's the first time I'm going to introduce the ICE table back into our discussion, which is that we can imagine what happens is when we take that solid and we put it in water initially, before the dissociation happens, we have no ions whatsoever in water of the insoluble salt, and we put the salt in there, mix it, it dissolves, then it dissociates, so it produces the ions according to the stoichiometry. So at equilibrium, we have X and 2X concentration of each of those ions. So the KSP would then be the product of Pb2 plus times I minus squared, which is just X times 2X being squared. So you end up being 4X cubed as the expression there, equal to KSP. The KSP is given already, so we can solve where 4x cubed is equal to 7.1 times 10 to the minus 3. So x here is equal to this number. And so what you have to think about is what that x represents. So in our ICE table, x represents the lead ion concentration. It's not, by the way, it's not the iodide ion concentration. It's just the lead ion concentration. But as it happens, x is of course also the solubility of lead iodide. Again, why? Because if you think about what solubility is, it's just the concentration of the dissolved salt. So it's this aqueous form of the salt that's dissolved in water before it dissociates. So that is solubility. But since it has a one-to-one stoichiometry with the lead ion, it's also the same as the concentration of the lead ion. So that's why once we found that number, that is also the solubility of the lead iodide. So I want to wrap up our discussion of solubility and KSP by giving you this pathway of converting from one quantity to another. So if you start with solubility, as we did with one of the problems, we can then convert that to molar solubility, just the molarity. So you might start with the grams per liter unit. Now we're converting it to moles per liter. And then you want to connect that to your ion concentration. And then the ion concentration would then connect to KSP, because KSP is given as the product of ion concentration. If you start with KSP, then you just go the opposite way. You go to ion concentration first, then you go to molarity or molar solubility of the compound, and then afterwards you can go to solubility of the compound expressed in grams per liter, okay?